class. Okay, so I'm in the one of the physics rooms, and I partially set up one of the labs that we would be doing in class, but I'm basically going to show you how this works, and then I'll give you all the data that you need. So to start out with, we have a track with this cart, and if I place the cart here, let it go, obviously it's going to accelerate down the track. And we want to measure the acceleration, and so I have two things here. First, I'll show you this device. This is called a photogate, and basically all it is there's a laser that goes like from one end to the other, and it can detect the laser if it reaches the other end. And so, like right now, if I plug this in, it would detect that there's a laser here. Now, on top of the cart, I can attach what's called a beam blocker. And there's several rows here, like this top row, there's like, these alternating black stripes, then there's thicker ones, but fewer of them, and then you've got these solid stripes. These are designed for different things. In this lab, we would use this top stripe. And basically what we would do in this lab is we would set up the photogate, and we have to set up carefully so we can adjust the height of the photogate, so we can raise it up or down. And we want to make sure to adjust the height so that, when this cart and the beam blocker pass through, it hits the right part of the beam blocker. So that's very important, but you're not going to be actually collecting the data, so you don't have to worry too much about that. But the idea is, picture this beam blocker going through. Let's start like this. Say that this top bar is set up, lined up with the laser. So like right now we're getting laser, the laser is being detected, but then when we cross, when the photogate block, or the beam blocker blocks it, photogate's going to notice that. So if you look at the intensity of the light that it's receiving, see if this marker works. So if we were to plot the intensity as a function of time, it would look something like this. Here's laser, here's no laser, nothing really in between. Now, you're never going to actually see this plot, but this is what the device is detecting, and there's a time interval here where the beam blocker is blocking the gate. And from that, we know how long, hold it up again, we're looking at this top bar. So we know how long it took for this top bar to basically pass through some point. Like the laser is basically a point. Well, it's a line, but we're perpendicular to that. And so the speed of the cart would just be the width of that, that black stripe divided by the time interval. Now, like I said, you're never going to see this plot. The computer can just register how long it took, like how long that laser was interrupted for, and it's also programmed in like how wide that bar is. And so it can, that photogate along with the beam blocker can be used to calculate the velocity of this cart. Now, what we're going to use in the lab, though, is this top row. So we have this sequence of stripes. And what we would expect in this case, the sequences are a lot, or the stripes are much narrower, and there's a lot of them. So if we plot the intensity as a function of time, we should expect something like this, where we'll have a narrower interruption in the laser, and then there will be some time again before the next stripe hits. And the next stripe is going to be narrower because the cart is accelerating down the track. And so it's going faster, so the laser will not be interrupted for as long. And also the time between these, let's call this delta T1. And this is delta T2. And like the time in between these interruptions is also going to get shorter. And each one's going to be narrower than the one before. And anyways, a computer automatically detects these and registers these time intervals. And I mean, you can set it up where you tell the computer how wide these are, but that's already been done for you. Like there's a file set up for this lab where that information has already been plugged in. So basically you run this and the computer is going to give you, remember each of these, we can calculate the velocity by just taking the width of that rectangle, dividing by the time interval. And there are several of these stripes that block the laser, so we're going to get several data points. And like I said, the velocity is increasing as a function of time, so like each one is higher than the next one. And so the computer, you run the experiment, basically you hold the cart up here, the photogate somewhere down here, and the beam blocker will be on the cart. And we release it, and then the computer is just basically going to bring up that velocity time plot with all these data points. And of course, if we find the best fit line, which the computer will do for us as well, the slope of that will give us the velocity. And so this is how we can actually measure the acceleration of the cart. And so what we're going to do in the first part of this experiment, I'm actually going to attach this photogate. Guess I should have just done this in the beginning, but do it now. Kind of a pain to set this thing up. Sorry about this, and we'll get it in a second. I wish I just did this in the beginning, but we'll get there. Yeah, okay, I'm going to hold this in place. Sorry about that. Okay, so what we're going to do, we'll have this beam blocker set up at a particular location. And you can't see it, but just permanently attached to the track is like a tape measure, so you can see distances. And what we're going to do is we're going to place this, like right now I placed it about 20 centimeters away. The cart is 20 centimeters from the photogate. And then release it, let it pass through, and record get a velocity time plot and measure the slope. And then from there, what if we say release it from 40 centimeters? So it's obviously going to be moving faster, but what about the acceleration? We have the same angle of incline here, but does the distance that we release it from, is that going to affect the acceleration? Now we know theoretically it should not. The acceleration should just be g times sine of theta. And so we're kind of testing that. So we're going to do 4 trials. First one, we're going to just release it and measure the acceleration. Then we'll have a different release point that's farther away, so it's moving faster when it goes through. So on that one, the data point should be all higher, but we would expect the same slope. And then another trial we're going to do is add a mass. So does mass affect the rate of acceleration of this cart? And again, theoretically, it should not. Just like in free fall, the mass of an object does not affect the rate that it's going to fall. And then we're going to do one more trial where we're going to lift up the track and change the elevation angle. So we change the incline, do it again, and is that going to affect the acceleration? So that's the first part of the experiment. We're just going to roll things down an incline and measure the acceleration, and do 4 trials by just varying something every time to see what effect that has. And then we should compare that to the theoretical results. Are we getting the results that we expect? And if not, try to explain why not. You can think of several errors. So yeah, that's one reason why we're doing this, where I'm actually showing you the actual experiment. Like, how do you know the angle of this? That's a factor in the experiment. So use a meter stick and just measure the height above the table. So like one end is on the ground. Like this end is on the ground. So here you can like measure the height and compare that to the length of the track. You have a triangle here. And you want to be careful that you measure from the table to the bottom of the track, because the bottom of the track here is on the table. So like one way you could do this wrong, although this won't be an error in your experiment because the data is given to you, if you measured from the table to the top of the track, that would be an error. But there's always errors with these kind of measurements. So that's one possible source. We're neglecting friction. That's another one. And yeah, we've talked quite a bit about errors, so try to think of a few. Always want to think about what measurements are involved, and all measurements have errors. And then other things like neglecting friction. Okay, so now that we've done part A, let's talk about part B. Or again, you can't see it too well, but I have something attached to the end of this cart here. And I brought out another one, just bring it over so you can see it. So this is a motion sensor, and basically it's sonar. It creates sound waves, and they'll hit the cart and bounce back, and it can detect those. So it's kind of like a radar, but using sound waves. And so what this does is it can measure, depending on how long it takes the sound to hit the cart and come back, it can determine the distance to the object. I didn't exactly set this up right. The thing should be like more on the track. This end of it has a little thing at the end, like a bumper to stop things from flying off. But it doesn't matter since we're not actually doing the experiment. So this would be set up at the end. And so what it's doing is measuring distance. And so what you would do is we start with the cart down at the end of the track and push it towards the motion sensor. So I just push it, and that would have been a bad trial because this doesn't work too well if you get too close to it, so it should maybe stop up here. But yeah, just do this, and that's all you do, and then the computer gives you some data. And again, I will give you the graphs that you need. But basically it's going to look, what it should look like, if we look at distance as a function of time, is it should look something like this. Because you start out far away. Now the problem is, the real graph probably won't look like this too much. Because you start out, like if I move it around here, that line on the left is going to be wiggling up and down. And then when I push it, the distance is decreasing, and then it's increasing. And then when I catch it, there'd be a very rapid stop. So it's going to kind of have this violent action at the end. But basically, the computer knows this. And so you have data that's going to look like this with kind of bad data. Like, you don't care about this part. That means nothing. You have to tell the computer to record data. So you hit start, and you could wait an hour, and it's just going to record that horizontal line for an hour because the cart's not moving, and then you push it. So basically, this part you don't care about. And then we don't want the cart flying off the track, so you catch it at the end, and it's going to detect that too. And so it's going to have this kind of, violent thing at the end, or this kind of extreme changes at the end of the motion. But what you can do is you can use your cursor, and again, this is what the graph looks like. It's actually data points, lots of data points. And what you can do is just move the cursor around and select the data points that you want. And again, this has been done for you. And so it'll kind of highlight those in yellow. And what it does then is it takes, like here, like the distance between these two data points, that's how far the cart moved. And again, these data points are equally spaced in time, and the computer knows the frequency of the motion sensor. And so it can use the distance between these data points to produce a velocity time plot. So again, it'll give you that as well. And again, this velocity, it's going to, ideally it would look something like this. The velocity is initially negative because you're pushing the cart toward, like the distance is decreasing. And it should look something like this. And then you can take the slope here. And from the velocity time plot, you can see the velocity is changing from one data point to the next, and it can use this data to calculate an acceleration time plot, which ideally would look something like this. It should be constant. So like the velocity should change the same amount in every time interval. Now, this is a part where, like, if you catch it at the end, we're talking it's moving relatively quickly and then it stops. So you can get like a huge spike of acceleration. But again, we have to carefully select the data. Now again, I'm drawing it as a bar, but it's actually going to be a bunch of like individual data points. There will be quite a few of them. And so in this one, what do you want to measure for your acceleration when you have several measurements that are all theoretically the same? So what we do is we tell the computer to take the mean value. So in this one, we're going to tell the computer to find the slope. In this one, we want to know the acceleration. So in a velocity time plot, we take the slope. But if we have measurements of the acceleration and several of them, we just take the average. And they should be the same. Like, we should get the same number for each of these two trials. And so again, that's what we do in the experiment, and you'll be given all of those refs. All right, and then there's one more part of the experiment, which I'll just show you. What we would do is we would set the photogate over the edge of the table. I'll do it this way so you can see it's, and then we drop this beam blocker. So this one is just equally spaced, uniform horizontal stripes. So we would drop it, and every time a stripe passes through, it's going to measure the velocity, and as the beam blocker is accelerating, the velocity should be increasing. And we're going to do two trials for that. One like I just did, where I held it right above and dropped it. And then we'll do another one where we drop it higher up and let it fall through. And that's basically it for this lab. Now, give you a little hint on the last part. So if I drop this beam blocker, let's see, I can get a good angle here. So here's the beam blocker. Drop it. It's not going to fall like perfectly perpendicular to the ground. Like, what if it has a slight angle? Is that going to give you an accurate measurement? Things like that. Or, here's an extreme case, if it falls kind of sideways like this. We kind of assume that it's going to just fall straight down. And if it was at an angle like this, or like that, or the angle could be a factor. So you want to think about that when you're writing up the lab report. Okay, but I think that's it for this lab. So I will send you the I'll put it on Canvas, the actual like lab report, instructions that we would have if we were doing this lab in class. And I will then give you all the data that you need, like all the numbers and graphs, like the mass of the cart, the mass of this thing. Basically everything you need, you'll be given that. So that'll be it for this lab.